Hello, my name is Joanne On,
And I'm Drew Niselak.
and for our CS 2316 final project, we're going to be taking an analytic look at coastal flooding and climate change in the United States, based on 27 different coastal cities given by the EPA. The point of interest and the purpose of this project was driven by our care and passion for the environment. We have chosen to analyze if changes in climate change have a direct correlation with the frequency of coastal flooding in the United States, based on 27 different coastal cities. Specifically, we have chosen to analyze changes in CO2 emissions and climate temperatures to compare the shifts with coastal flooding data over the course of both the 1950s until now and also from 2008 until 2018. We're going to be focusing on answering the two questions throughout the presentation. Does climate change have a direct correlation with the frequency of coastal flooding, and what extraneous factors could lead to a lack of or increase in tangible environmental change? We hypothesize that climate change becomes an increasingly pressing issue within our own nation and world, and it's imperative to do all we can to combat the detrimental environmental change for the sake of the Earth's inhabitants. By evaluating real-world data on climate and changes throughout the years, we're going to be able to provide helpful insight into what kind of direct effects are done onto our country based on climate change, and we hypothesize that there is an increasingly pressing demand to enact change for our country. For our data collection, we took a look at government and trusted websites for climate change, CO2 emissions, greenhouse gas emissions, and coastal flooding data. We analyzed 4 different data sets. One from the EPA website, which was a CSV file that shows 27 different coastal cities and their flooding averages from the 1950s and 2010s. We chose a CSV file from Our World in Data of CO2 data from locations around the world. From Statistica, we chose an HTML data showing annual average temperature in the United States. And finally, we chose an API from Climate Azavea, which showed precipitation rates and daily average minimum and maximum of cities within the United States.
For the EPA CSV, we had to use CSV Reader to convert the CSV into a list of lists, and then we changed strings to float values. For Our World in Data CSV, we again used the CSV Reader. We had to change some strings into floats and some strings into integers, and if the strings were empty, we simply changed them to 0. For Statistica HTML, we used Beautiful Soup, and we had to pick out year and temperature because those were the 2 data points that we needed. For Climate Azavea API, we used the request module, request.get, and JSON to find the minimum and maximum temperatures along with precipitation values each year from 2008 to 2018 based on 1,621 cities, and we found those based on city IDs. Now we will take a look at our data insights and data visualizations. For our first insight, we looked for a correlation between CO2 emissions, average annual temperatures, and coastal flooding. The graph on the left shows CO2 emissions per year in the United States. The center graph shows average temperature per year in the United States, and the right graph shows the average floods per year, the blue bar being the 1950s and the red bar being the 2010s. What we concluded is that there is a correlation, and a positive correlation, between each of these 3 statistics. Our second insight compares CO2 emissions and greenhouse gas emissions in the United States. CO2 emissions increased until about 2005. That trend is further confirmed by greenhouse gas emissions data, which shows a downward trend in the same time period. The far right graph shows a negative correlation between time and percent change of CO2 emissions. In approximately 2005, the percent change turned negative, meaning that CO2 emissions per year are starting to decrease.
Our third insight takes a look at the average daily minimum temperature for all 27 cities. We're going to look at 2008 and 2018 and see that there is a slight increase in the temperature between the range of this time. If you take an example and look at the pink dot in the center, it has shifted a little bit to the right compared from 2008 into 2018. The average daily minimum temperature is also referred to as TASMIN. These 2 scatter plots show a similar trend for the TASMAX, which is the average daily maximum temperature. These two scatter plots show the 2008 maximum daily temperature and the 2018 average daily maximum temperature. And we also see that there is a similar trend, an increase. If we take a look at that same similar pink dot in the center of the graphs, you can see that it has shifted a little bit to the right. This is a similar trend for all the 27 dots for each scatter plot, if you look at the difference between 2018 and 2008. Finally, for precipitation rates in 2008 and 2018, there is also a similar rightward trend in both of the scatter plots for all 27 cities. Overall, we can see that there is a slight increase for TASMAX, TASMIN, and precipitation rates for all 27 of these coastal flooding cities from 2008 to 2018.
As a part of Insight 4, we tried to explain the variance in the difference in average floods per year between the cities. We thought that average precipitation per year might explain some of that variance. However, given that most of the coastal cities average the same amount of precipitation per year, and the variance in average floods is still so great, precipitation does not seem to explain variance in difference of average floods. The data from these graphs clearly show a decrease in CO2 emissions and greenhouse gas emissions around 2005. For Insight 5, we tried to explain that decrease starting in 2005. An article from Berkeley Earth gave multiple reasons for the possible decrease in emissions. Some of them could have been companies switching from coal to natural gas, more fuel-efficient cars, more environmentally conscious people, or even finding alternative energy sources. All of these factors contribute to a potential decrease in CO2 emissions. Data Visualization 1 places average temperature in the United States and CO2 emissions in the United States on the same graph. The purpose of this data visualization is to show how when CO2 emissions increase, so does average temperature. Data Visualization 2 compares greenhouse gas emissions and CO2 emission percent change. As we previously stated, it seems to be around 2005 that greenhouse gas emissions decrease and CO2 emission percent change begins to turn negative.
For our third data visualization, we took a look at scatter plots for all the years 2008 to 2018 when comparing the 27 cities between their TASMIN, TASMAX, and precipitation rates. In our code, we showed 30 more scatter plots just like these for all the different years. In this slide, we show the scatter plots for the year 2008. And when you compare all the scatter plots over time, we find that there's a general slight trend in increase for all the values over time. Generally, when you compare 2018 to 2008, there is a slight increase. Despite the fact that there might be slight changes between the years in 1 year intervals, whether that is increase or decrease, there is generally an increase when you compare all the values. At the beginning of our presentation, we hypothesized that CO2 emissions were growing at an exponential rate. We found that global warming is a pressing issue and we as a society should continue to fight against it. However, some of our efforts are being shown to pay off. Based on our data collections, we were able to find that climate change is indeed continuing to progress in our country over time, seemingly allowing for CO2 emissions, greenhouse gas emissions, and average temperatures to all increase. However, by analyzing our data from the past 10 years, CO2 and greenhouse gas emissions have been seen to be on a steady decline, whether that is due to alternative fuel sources or environmentally conscious consumers or businesses, all in our country. There is a correlation between coastal flooding and temperatures, but the correlation is not as strong as we thought, with a correlation coefficient found to be 0.54. We hypothesize that as these emissions are on a downward trajectory, temperatures may increase at a slower pace than previously imagined. In one way or the other, our data displays that the reality of climate change and global warming is true, but perhaps at a surprisingly slower pace than we may have thought. Even so, it is imperative for us to continue to do all we can to help combat environmental damage, such as coastal flooding and increase in global temperatures, and perhaps even use computer science to do so.